Thanks very much. I know we're probably running a little bit behind time, so I'll try to speed things up a little bit. I'm going to give my perspectives today as an academic statistician. My career has spanned two countries, US and Australia, so I'll talk a bit about that. I'm also representing ASAMS, which is our fairly recently funded Centre of Excellence in Mathematical and Statistical Frontiers. And see Shelley laughing at my joke. I can't actually deliver a joke well, but I find good cartoons. So I've actually, as I've been sitting over there and looking at the ASAMS banner, I've actually found myself thinking several times of Peter Hall, who was our founding director of ASAMS, and we had many, many arguments at the beginning as we, planned it out and so on. And he was the one that came up with the idea of having the S in the shape of an integral sign. But I feel a little bit sad because I think Peter would have absolutely loved today, and I think it's great that we're doing this. So why do I love being a statistician? I always go back to one of my heroes, John Tukey. I had the privilege as a very young statistician to be working on a project where he was one of the advisors, and he just was pretty inspiring. He was quite an amazing theoretician, but he really cared about data and the practical things. And one of the quotes from him that I really like is that being a statistician allows you to play in other people's backyards. And that's a thing that really resonates with me as well. And I think for me, I've always loved to think about that theory and practice, theory and methods to practice gradient. And I think getting that right is really part of the challenge and the beauty of our field. There are some people who really are talented and love doing the theory and methods, and of course Peter Hall comes to mind there. There are some people who love getting out there and getting their hands dirty with data, problem solving. But for me, and I think for a lot of the academic statisticians, the sweet spot is that blend of both. And that's what I've always liked. So I like to think about this virtuous collaboration cycle, where it's when you get engaged in real-world problems that you really start to get inspired and get ideas about statistical methods, things that you can do. When I was a graduate student, I was doing my PhD in statistics, and I don't think I ever actually looked at a data set. I was in Shelley's department then, but I don't think I actually looked at a data set during my PhD years. And I remember in the last year, I'm like, oh, this is just torture. And because I was a grad student, I would pack my lunch each day and go into work. And by about 10 o'clock, I'd be looking at my watch, is it lunchtime yet? And I usually would have eaten my lunch by about 10 o'clock in the morning just because I was, watching the hours tick by. It was difficult. It was that feeling of isolation. But when I went to Harvard Biostat for my postdoc, that's when things turned around, because that's when I learnt about collaboration. And the situation there, and I think it was really absolutely world leading, and I learnt a lot from my years there. You would be part of a team, you'd be with medical doctors and epidemiologists, there was the database people, computer scientists and so on, and you'd be working together to try to solve a real world problem. But you would get ideas, methods, statistical, mathematical ideas. You would then have the time carved out as part of your job that you could go back and work on those theories and methods, come up with new approaches, bring those back to the problem, and then that would provide better solutions. So it's that virtuous cycle. To me, that's the absolute key of world-class academic statistics. I'm going to come back to this point a little bit as I go along. Just very briefly, just to give you a concrete example, one of my long-time favourite projects, this is a project from probably a good 15 years ago, but we were helping a colleague who was a social epidemiologist, had designed a school-based curriculum to get kids to watch less TV and be more physically active. And the kids would fill out questionnaires about what they did and so on, but they'd also wear these little accelerometers, a little bit like my Fitbit today. And so the data set, it was actually an early example of, in a way, what you might talk about as big data today, because the data on each kid was quite voluminous. And it was really hard to figure out how to analyze it. So we had great fun with these data. We managed to come up with some new theory where we did it was an analysis of variance, but it was based on a wavelet decomposition, so it was a bit cool, and we managed to have a PhD student do her thesis involving that approach. We got a good paper in one of the good stats journals, but more importantly, we helped to answer the study questions, and we learned other things as well, like how to do good visualization. This is just the heat maps with the activity levels measured from the accelerometer by time of day for a couple of kids. And you can just see what the kids are doing. You can see where they get up in the morning, start moving around a little bit. They then go to school, and you can see that they're basically sitting motionless during class, and then they change to go to a different classroom. You can unfortunately see how inactive they tend to be once they get home from school, sit and start watching TV. So we had a lot of fun with these data. So I think it was a great example where we had that virtuous cycle going on. So just then, by way of a little bit of contrast, and I thought a lot about, as I prepared for this presentation, should I be positive or should I say some less positive things? So I've decided I'll say a few things which I think are not so positive. My experience in the US was that there is very much a culture of collaboration there, at least in where I was. And I think it's true that it's been helping the statistical sciences to thrive in the US. And we've seen that from some of Xiaoli's numbers. I was impressed with the numbers at Harvard College from his presentation, but then one of the later presentations showed similar graphs from US-wide. So I'm still impressed with Xiaoli, but we see that definitely the trends are really positive in the US. For me, having been back in Australia now for 7 years, I'm sorry to say that it's been quite a different experience, and I have found it very, very difficult to try to find that same collaborative environment back in Australia. So what I'm going to do now is talk about some of the reasons, and I don't want to be negative, but this is opportunity to be provocative, so I decided that I would do that. So I want to talk about some of the reasons why I think it's so difficult, because I have to say, these last 7 years, career-wise, have been extraordinarily difficult for me and a bit depressing, to tell the truth. So I think one of the core problems is that science is changing. It is becoming increasingly multidisciplinary, and it is becoming data intensive. So I think part of it is around the fact that we are in a period of disruptive innovation. I looked up the Bible on Google, which was Wikipedia, and it gave the definition. It's a good definition: disruptive innovation, which was invented by Clay Christensen from Harvard Business School. When I was at CSIRO for a couple of years, and they realized that I might be an okay academic statistician, but I was hopeless at managing a division at CSIRO, they sent me off to Harvard Business School to see if I could learn some skills about management. But I learned some interesting stuff. One of them was about disruptive innovation. So it's an innovation that creates a new market and value network and eventually disrupts an existing market and value network, displacing established market leaders and alliances. So I think if you think about that definition, you'd have to admit that the whole explosion around the broader sense of data science, the computer side of things, is having a disruptive effect. Now, what that means is that there's been massive changes in the statistical field. I actually remember this picture I've got up on the top right-hand corner there. It's Steve Lagarkos's old, was one of the very first, they called it a laptop, but you'd be really hard-pressed to put it on your lap. And I don't know if any of you have seen like portable sewing machines. You lug it around. It's a good 20 kilos. So that was the first laptop, and I remember that. And that's not so many years ago. So the way in which the computing world has changed is just astonishing. We're seeing a lot of these new fields emerging: bioinformatics, analytics, machine learning, data mining, data science, and so on. And it's having a big impact. Our field, if you think of statistical science, we have changed, but in my opinion, we need to do a whole lot more. It's not enough for someone to understand the theory anymore. you absolutely have to be abreast of the modern trends in data management, computer science, and so on. And we've heard that from several of our presenters this morning. When they're talking about, you know, the data revolution, they're actually more often talking about the computer science than the statistical science and the mathematical science that you need to analyze the data. So we have to get our act together to embrace that, the computer part of the world that we're in. So you might be saying at this point, well, that's not just an Australian problem, that's a global problem. And that's absolutely true. It is a global problem. But I do think that there is a couple of characteristics of the Australian environment, and I don't know about the New Zealand environment. It's part of Australia, right, New Zealand? So, but I do think there are some features that make it more complicated.
West Island.
Oh, okay. So one of our biggest problems is we lack critical mass. That is a big issue for us. I tried to do a little bit of a survey of the university offerings in statistics and trying to get a little bit of a landscape. It's actually quite difficult to do that. But I found that in general, stats is usually bundled in with mathematics, and increasingly it seems like there's like this collapsing, like we're now bundled in with here at UTS, where not only are we bundled with mathematics, we're bundled with physics and chemistry. So I think that's that kind of trend. So I found that almost ubiquitous that stats was in with maths. And I think if you go to the US, you don't see that. Macquarie is one of the standalones that I could find. They're having a standalone stats department. There are also places that bundle stats in with finance and economics and so on. With a couple of exceptions, and this I think is a massive problem that we have to think about. A couple of exceptions, maths and stats are generally quite separated from the computer science, and I think that's a big problem. We have to find ways to traverse that gap. So what we find is that none of us have much size. Macquarie's a decent size, but I think the rest of us, we're struggling to get that critical mass, and that is definitely one of our problems. The other problem, or one of the other problems, is that our major funding body, the Australian Research Council, I just pulled these numbers off the web yesterday, and I just have a graph here. It's on the log scale, and it's looking at just the total number of ARC grants awarded by year. The green is discovery grants, the blue is early career awards, which I think looks like there was a bit of a bump, but it's declining laureate. So you see that it's declining or flat at best. This is, again, on the log scale, number of grants in statistics in green, mathematical sciences in general in red, and then all. And you see that overall, I think there's a bit of a decline, but maths and stats, we're just not getting a lot. And you can see by the numbers, it's not a lot. So critical mass is a big issue for us. I also think that the ARC funding model doesn't really help with what we're trying to do. It seems to me that the system is skewed towards individual investigators. The kind of activity I think that really makes us thrive as a discipline is that interdisciplinary, collaborative, engaged, virtuous cycle of collaboration that I talked about before. That kind of research very easily falls into the cracks. Very hard to get that kind of funding. There's very little direct support for interdisciplinary work. And also a big problem is that unlike US grants, there's little salary support for us. You get support for your students and postdocs. But if you're trying to do collaborative, interdisciplinary work, it takes a lot of time. You can't just do it on the side. So the whole system is skewed towards individual investigators. The typical university model doesn't help either. It's not really clear how do you really value interdisciplinary work. The faculty structures often create silos. I would love for us to be much more closely engaged with the machine learning people, but they're in the faculty of engineering and IT here at UTS, and it's just difficult. Everybody wants to be a center director, and so you get a proliferation of these things that, yeah, anyway, don't get me started. So should we just give up? Is it just too depressing? Some days I feel a little bit this way, but on the whole, no, I think that there's a lot we can do. So one is to develop new models of collaboration. And I want to point here, it's actually not that new a model. We have John Carlin sitting here from Melbourne, and hopefully John will get a chance to say a few words. The Biostatistics Collaboration of Australia, I think, is absolutely brilliant. It is highly innovative. They've survived now for about 15 years, and I know what their funding model is. They run on the smell of an oily rag. It's just astonishing. They run because you've got a few passionate people who believe in it. But we don't have time to go into it in great detail, but it's a really innovative way to overcome some of that critical mass problem by having universities collaborate in offering courses. So you don't have to have every university trying to offer all the same courses, but you can share the course offerings. So that's a model. This is from the BCA external review, and I'll quote this because I think I wrote it back in 2004 where I was chair of the review committee. So the BCA offers a more comprehensive range of courses in biostatistics than any other Australian educational institution, and the breadth and depth of its curriculum is comparable with many traditional residential master's degree training programs in biostatistics around the world. So it really is quite astonishing, and it shows what can be done with a tiny bit of funding and a lot of passion. I think we can continue pushing our heads of schools. Well, ours is already on board. We don't need to do that bit, but we need to push our dean to value interdisciplinary work. We need to seek effective industry and government partnerships. I think just relying on ARC and government funding is not a good idea. Just a little example. This is one project, one of my projects that I've really enjoyed since being back in Australia, and we got a bit of funding from the New South Wales Environmental Protection Authority, where they needed some help analysing some data looking at dust levels in the rail corridor up in the Hunter Valley. And it was a great project in that it was very challenging. The data was from air pollution monitors. We had a ton of data. So it was quite challenging. It was like a kind of a big data problem. We had a good time doing the analysis. I've got a PhD student now working with me and Scott Sisson on a cool new technique called symbolic data analysis. We prepared a report for the EPA, which hopefully was helpful to them. So I think this was a good example where we could engage, get a bit of funding, and progress both the practical and also the methodological. We can definitely lobby the funding agencies to properly support the interdisciplinary research. And I know as part of the decadal plan, there's been a recommendation to establish a national centre for the mathematical sciences. And I think that getting that interdisciplinary engagement in there is really key. And I think we can tell a fantastic story. It's so compelling if we can just get it to the right audiences. There are funding models that work. Now, this is from the US. We used to get a lot of funding in our biostats group from various centre and program project grants from the National Institutes of Health. That was our primary funding source, a little bit like NHMRC here. Now, the NIH there, they recognised that interdisciplinary research was critical, but they recognised that you can't just do it on the side. It takes resources to support it. So they would have these centre grants that would provide the infrastructure to get that done. And it would give you some funding to put people on projects, but also to push the methodological boundaries. It really suits well the enabling disciplines like statistical science, mathematical sciences, and so on, because you can create a core where you've got a blend of just plain old support, collaboration, new methods research, training. It's got the whole thing in there. So that was one example. Again, pointing to John Carlin, there has been an example of this exact kind of thing recently funded, well, a few years ago funded, and unfortunately I think not getting renewed, which is terrible. The Vic Biostat, which is an NHMRC funded centre, doing exactly this same thing, building core methodology around statistical and biostatistical sciences to enhance population health. It's a fantastic thing. We need more of these kinds of efforts, but they've got to be sustainable, and you can't just have them disappear every few years. ASEMS, I'd like to say just a couple of words about ASEMS. It's our recently established Centre of Excellence. I could spend a lot of time talking about it, but I just will say one thing, that one of the core goals of ASEMS was to try to create a centre that allowed us to traverse that theory-practice gradient. Peter Hall and I used to talk about that a lot. We had some quite heated arguments about how to focus the centre. I just wanted to give a couple of my perspectives about how I've been able to use the funding that's come to me as a centre investigator. So I really do believe in this kind of embedded training model. So I've used some of my postdoctoral funds to leverage that with funding with external partners. So I've got 3 of them. One spends 60% of her time with the Sachs Institute, one spends 50% of his time with the Australian Red Cross, and one spends 50% of his time working on a Gates-funded project with me. All 3 of them have to spend a lot of time really getting their hands dirty with data and really solving practical problems. But then they're supposed to identify new methods challenges and push the methodological boundaries. So they've got that blend. They're learning to communicate better. And I have to say, particularly, I hope Stephen and Craig aren't here, because I want to say Joanna in particular is just one of the most spectacularly polished presenters I've ever seen. So she's just great. So I'm excited to see for all 3 of them where they'll end up going with their careers. So there is a lot we can do. Breaking down the faculty silos, obviously we need to really connect with our mathematics cousins, but we need to connect with the computer scientists, the machine learners. We need to connect with our domain colleagues as well, people in business, environment, medicine and health. We've seen some good examples in my brief presentation about some of the things that work, but it takes funding, but we need to create that vision for what will work and just lobby hard to get that funding. Industry engagement is absolutely critical. Our mathematical colleagues are key, but I have to say, I think our computer science colleagues are every bit as key. We absolutely must engage better there. And if we don't, we're just going to miss the boat completely. We have to get much better there. And that's not just with our next generation of students. We have to retrain ourselves as well. And through the Stat Society, we try to do a lot of that, giving ourselves workshops on Hadoop, what's Hadoop, and things like that. I think that AMSI is absolutely key, the National Committee for Mathematical Sciences, and I'm really excited that they're eagerly awaiting our report as they see it as a first step in an implementation strategy for achieving the goals outlined in the decadal plan. The Stat Society can do a lot in reaching out to other places, and Longbing I think is up there. Yep, Longbing was just handing me this thing yesterday where the American Statistical Association is collaborating with the IEEE to co-sponsor Data Science and Advanced Analytics Conference in Montreal. That's the kind of thing we need to be doing. Some of that's happening, we need to do a lot more of it. And so look, I think I'll stop there. With one final cartoon to amuse Xiao Li, and I'll stop there. Thank you.